Okay, so for this, we're going to look at a few examples. Last time, so we're still looking at parametric equations. In the previous class, we saw questions where we were given equations in terms of t, and we saw how we sketch those curves. The first step was to combine those so that we represent them in terms of x and y. For this class, we see that we have parametric equations also given, but this time we have trig ratios involved. Now, how do you work out such questions? So mostly when you have trig ratios involved, you're going to depend on trig identities. And what are some of the most common trig identities that you're going to see? Well, you have the main trig identity, and the main one is sine squared theta plus cos squared theta is equals to 1. So this is the main trig identity. Now, there are a few more trig identities that you're going to find helpful here, but this is the key one that you're going to depend on. For example, the first question here works on that. Now, how do we use that identity to solve or create the sketch for these parametric equations? Okay, so to understand the curve represented by these parametric equations, when they are independent like this, it might be difficult for us to picture them, but we want to connect them. How do we connect them? Well, here we utilize the fact that if we had sine squared theta and we had cos squared theta, if we had these, if we just added them, we know to say this would give us 1. Well, if you look at the parametric equations, 1 is the definition of cos theta. The second one is the definition of sine theta, meaning I'll get the first one, and for this first one, I'll square the left side and the right side, meaning that now I will have x squared is equals to cos squared theta. In the same way, when I get the second parametric equation, and just like the first one, I'll square it, so I'll have y is equals to sine theta. When I square both sides, we'll have y squared, and on the right side, we'll have sine squared theta. So notice that I haven't changed anything in terms of my parametric equations. I've just squared both sides for each one of them. After doing that, now we can do this. See, get the left-hand side. If you get the left-hand side, add them. So for these two equations, I'll add the two equations. So if I add this and this, I have x squared plus y squared. Now I will add the right-hand side. So I have equal. From the right-hand side of the first one, I have cos squared theta. And then the second one here, I have sine squared theta. So this is where we are now. But then we recall that this part, cos squared plus sine squared, that is basically 1, meaning that the left side remains this, but the right side reduces to 1. So now we have combined our two parametric equations into one equation that relates x and y. Now, the only part that maybe could have been confusing is that part where we had x squared is equals to cos squared and y squared is equals to sine squared theta. So here, all I was doing here was just solving two simultaneous equations. Basically, I just added, so you can always add these two equations, but to add them, you add the left sides and you add the right sides together. So I added the left side, I had x squared plus y squared. Then I added the right side, I had cos squared plus sine squared. Depending on what you need, sometimes you can choose to subtract the two equations. But in this case, of course, we did need to subtract. Addition was the best step. Any questions up to here? Go ahead.
When do you subtract?
When do you subtract?
Yes, this is the question.
Okay, in this case, it depends with the question that you're looking at. Let's see, we'll look at the second question that you have here, and we'll see if it would need a subtraction. Is it this one? No, I think maybe in the next question or so. This one might not need that. This one will not need that. But I think for this one, looking at the identity we are going towards, we don't have a subtraction showing up. I think we'll try to find more questions that when it shows up, it will be easy for me to relate. But for now, I know to say if I had cos and sine squared adding, this would give me a 1. So I took advantage of that. What would end up on the left side is of no consequence. The key was I knew that these would end up giving us a 1. There's an example that is in front that has a negative somewhere. I think you'll see it when we reach it. But I'm not sure if it will answer your question. Any other question? Okay. So we haven't answered the question yet. We have only combined the two parametric equations into an equation that we can actually understand. When they were independent in terms of theta, it was hard for us to picture them as what the curve was really. But notice that by combining them, now it's easy for us to see what this curve is all about. And looking at the equation that we have, x squared plus y squared is equals to 1. This is an equation of a circle. So sketching it becomes easy. So you have the y-axis and the x-axis. So since this is an equation of a circle, and in this case, notice that this circle is centered at the origin. So our circle is centered at the origin, something like this. And based on what we have on the right side, we can conclude that the radius of this circle is 1. So we can conclude that the radius of the circle is a 1. So because the radius of the circle is a 1, we see that here, this has to be at 1. This has to be at -1. This has to be at 1. This has to be -1 because the distance from here to here, sorry, not that. From here to here, this is 1. Okay, so basically this is what we have. This is how you answer this question. Any questions so far? And the key thing here is, when you look at this range here, they're saying for theta less or equal to, for 0 less or equal to theta less or equals to 2 pi. So here our theta is an angle. If I drew my radius here, it's an angle from here up to there. This is our theta. And they're saying theta is from 0 all the way up to 2 pi, meaning that it's actually a full rotation creating our complete circle. Had our theta been maybe from 0 less or equal to theta less or equal to pi, then this would have been a semicircle, because we know to say pi would have been made by just rotating from here up to here. So we would have just ended up with the upper piece of our circle. But for this case, since we're going all the way to 2 pi, it's a full rotation. Okay. Now let's go ahead.
On the pi,
Yes.
which pi is on the y-axis? Is that pi over 2?
No. Angles are measured from the positive x. So if it's 0 to 2 pi, then we start from here. This is half pi or 90 degrees. By the time we reach here, it's now pi, meaning 180 degrees. By the time we reach here, this is 3 pi over 2. Yes, 3 pi over 2, which is 270 degrees. But for us to make a complete circle, this is 2 pi. Have you got it?
Okay, so that's 3 pi over 2. That's the bottom.
Yes, 3 pi over 2. If it was from 0 to 3 pi over 2, this would have been something like starting from here, just up to here. You've seen that?
Yes.
Okay, so we move on to the next example. And for the second one, let's see what we are looking at. So you have a similar idea. We still have trig ratios in this question. But how do we approach it? So again, we want to take advantage of identities. So we still see cos and sine present. So if only we could have a way of using that first identity. We know to say in using that identity, it depended on us ending up with sine squared somewhere, then with cos squared somewhere being equals to 1. Meaning that somehow the sine and the cos must end up being squares. So we can actually start even here. So maybe we should square each one of these. If I square the left of the first one, I get x squared. If I square the right of the first one, I have to square the 3, which becomes 9. Then I have to square the cos as well, which becomes cos squared theta. Are we okay with that first one?
Yes.
Great. So we now do the same thing with the second one. When you square the left of the second one, we get y squared. When you square the right side, first you square the 4, which becomes 16. Then we square the sine there, which becomes sine squared theta. So sine squared and cos squared have appeared in our expressions. But notice that they are not on their own. We still have the 9 here, and we still have the 16 there. We only want cos this side so that it's easy for us to add them. So they give us that 0, that 1 we want in that identity. So meaning to this one, I'll divide both sides over 9. Notice that this 9 would cancel here, leaving me with x squared over 9 is equal to cos squared theta. I can do the same thing to this one. I'll divide both sides by 16. If I did that, the 16 here would eliminate, leaving y squared over 16 being equals to sine squared theta. Notice that now it's in the perfect shape where we can add the respective sides. So if we get this and just put it down here, now I can say, let's add our equations. So to add these, add the left sides. So from the first one, the left side is x squared over 9. Plus, from the second one, the left side is y squared over 16. Equal. From the first one, on the right side, we have cos squared. And then from the second one, we have sine squared. So notice that in my definition of the identity, I had sine squared plus cos squared being equals to 1. Here it doesn't matter whether you start with sine squared plus cos, or you start with cos squared then plus sine. The same thing. So here we have this. Again, this is what simplifies to become 1. So this is the equation of the curve we're looking for. So earlier the curve was given in terms of its parametric equations. These were the parametric equations. But we have combined them so that now they appear as one equation. And this is the equation that we are looking at. Can you guys identify what this equation is? What is this equation giving us? This is an ellipse. Now, can you say more about this ellipse? What else can you say about it?
Its major axis is in the y.
Yes, the major is in the y-axis. To understand the major, you identify the bigger denominator. This only applies for an ellipse. The bigger denominator is with y, so the major axis is in the y-axis. So remember, the major axis is going to be the one that tells us what a is, or what a squared is. Okay, so this is what we have. Sketching an ellipse, once you understand where the major is, becomes very easy. So how do you do it? So first, I just want to indicate the key parts. This is y, this is x. So sketching an ellipse is easy. Since the measure is in the y, I'll just do this. But we now just have to indicate the key components. Since this ellipse is centered at the origin, if it weren't, we would have something adding or subtracting to our x, and also something adding or subtracting to our y. Because nothing is happening there, we know that this is centered at the origin right at 0, 0. So we know to say A gives us where the vertices are, and as I pointed out, the major axis, that is where A is going to come from. So we know that A squared is equals to 16. So A has to be plus and minus 4. So the upper one will be plus 4. The lower one will be minus 4. Any questions so far? Okay, looks like we're okay. If you want to give, yeah, go ahead.
The question on the equation, final equation, x squared over 9. The square is multiplying the denominators.
Pardon?
Yes.
Oh, you mean this square here?
Yes.
No, it's not. If you remember the standard formula for this conic section, you have x squared over a squared plus y squared over b squared being equals to 1. This is the equation of an ellipse whose measure is in the x-axis. Now the logic here is whatever the denominator of the x squared here, in this case, will be equal to a squared. Do you get that?
Yes.
So in our case, the measure was in the y, so we're looking at this setup. So then the logic dictated that whatever the denominator of the y squared was going to be equal to not a, but a squared. This is why I said a squared is equals to 16.
Yes.
You get it?
Yes.
Great. So in the same way, b, not b is equals to 9, but b squared is equals to 9. You get that?
Yes, sir.
So b will be equal to plus or minus 3. So that this part is minus 3 and this part is at 3. Just doing this is enough for our ellipse, so we have completed our question.
So you don't have to include all this the foci?
You can include it if you just want to be, if you want to be thorough, but the question was only asking us to sketch the parametric equation. Notice that under conic section, they'll say and state the foci, vertices, and so on. They will actually, I mentioned to you, but here the goal was only to trace where this curve is passing. That was the aim.
Just in the case that we're asked to do the foci, how quick is it, or how easy is it to what we have?
So seeing that we know what a squared is and that b squared is equals to 9, getting the foci is easy. The foci is given by c. For an ellipse, you know that b squared is equal to a squared minus c squared. This is if you're dealing with an ellipse. If you're dealing with a hyperbola, you have b squared is equal to c squared minus a squared. This is if you're dealing with a hyperbola. So this is for an ellipse. So since we have b squared as 9, a squared as 16, so finding c becomes easy. C becomes positive this side, 9 becomes negative this side. So we now have c squared is equals to, when 9 is less from 6, we remain with 7. So that c will be equals to plus or minus root 7. C tells us where the focus is. Since C is root 7, it tells us that the foci will be here at positive root 7, and the other foci will be down here at negative root 7. Have you got that?
Yes.
Okay, so we can now look at another example. So in the examples we've done so far, we're looking at parametric equations where the first step was to combine the given parametric equation to give the combined equation that has x and y. But now we want to look at equations where you are given the equation itself where you have x and y, and now we want to get the parametric equations. So look at the first one, for example. In the first question, they're saying, find a set of parametric equations that represent the graph of y is equals to 1 minus x squared. So see, they've given us an equation that describes a curve, but they want us to find the corresponding parametric equations that describe the same thing. But look at this. You see, in obtaining parametric equations, it's all about the parameter. What parameter are you going to use? For this question, they have specified. What are they saying? Using the slope m as the parameter. You see, the parameter here has been defined to be the slope of dy dx, where y is the expression they've given us. Then they're given at the point x, y. So how do we do this? How are we going to get these parameters? Well, first, let's find what that parameter m is going to be. So we have y. The equation that we've been given is y is equals to 1 minus x squared. So our parameter is described as m is equals to dy dx. Since this is y, let's differentiate it. The derivative of 1 is 0, so the minus will remain here. The 2 comes down here, and then the power of the x reduces by 1. So this is what we have here. So we have m is equals to negative 2x. See, now we have the relationship between m and x, and our parameter is m. Now look at the other questions where they gave us the parametric equation. How were they writing them? Notice that the parametric equations were in terms of x written in terms of the parameter itself. So x was written in terms of theta here, y was written in terms of theta. Even in the other case, you observe that when it came to parametric equations, you had the variables x and y written in terms of the parameter we're dealing with. So in light of that, since we have a parameter here relating to negative 2x, we can actually now just write this so that we have x written in terms of that parameter. In other words, we just have to make x the subject of the formula. To do that, divide both sides by negative 2. And if we did that, we end up with x is equals to negative m over 2. Well, believe it or not, this is actually the first parametric equation. All we have to do now is find the second one. Now, to find the other, all we have to do is substitute. Since we already have the relationship between x and y, we can now just substitute these, the expression for x in the main equation. So here, where there's x, we'll put that parametric one will be found, which is 1, becomes 1 minus, then we have minus m over 2. So we just have to simplify this now. Okay, so we have a square. Yeah, the x here is squared. Based on that, this is now y is equals to 1 minus, when we square here, the negative will be squared to positive. The m will now be m squared. The 2 will now be 4. So notice that again, we now have the second parametric equation, the one for y. So we can now create our conclusion. The first parametric equation was in terms of x. and this was x is equals to minus m over 2. The second one was in terms of y, and this was y is equals to 1 minus m squared over 4. Now, in all the questions we did earlier, we sought to say we had a control where we could specify how the parameter was changing. In this case, when you look at what we're dealing with, we see that the values of m can acquire any value. So we can conclude that for this case, the values of m can take the whole set of real numbers. So I can say from negative infinity all the way up to positive infinity. So these are the values of m. So for m belonging in this set. Okay, so this is what we have. So any questions before we proceed to the next example?
What was the question asking?
The question was asking us to get the parametric equation that represent this scale. So we have found the two parametric equations.
All right, sir.
Okay. Look at the second one here. In the second question, now we're seeing that they're saying find the parametric equations. Sorry for that. Sorry for the noise in my background. Okay. For this example, they're now saying find the parametric equation for the right-handed branch of a hyperbola. So, yeah, Bellington, I think for the question that you asked, a hyperbola in most cases would require us to subtract. Now, to the exact state of what x could have been defined as and y, you will see the answers we'll find here will be the ones that would require this to be a subtraction here. You'll see, I think I'll bring it back once after we're done with that. So we want to find parametric equations that describe this right-handed hyperbola. So how do we do it? For this one, we will have to depend on trig identities. But now we need one that has a subtraction here. Do you guys remember any trig identity which utilizes a negative? Well, think about it like this. The original trig identity, the main one, was this. And then this was equals to 1 here. So this was the original one that we started with. So there are a number of trig identities that you can come up with. Most of them will start from here. The other trig identity that you need to remember, now this one will have a minus, which is the one that we're going to need. This is going to be in terms of sec. So if you have sec squared theta, and then we have minus tan squared theta, this would be equal to 1. So if you wanted to come up with this trig identity, again, you can come up with it from that first one. Let me show you how. So look at this trig identity. If you can remember this, now what you have to do here is, since you want to end up with sec here, just divide through, because sec has to show up when 1 is on top and cos is down here. So we're just going to divide through the left side by cos squared theta, and we'll divide the right side also by cos squared theta. If we did that, we now have sine squared theta over cos squared theta plus cos squared theta over cos squared theta equal to 1 over cos squared is going to give us sec squared theta. So that is what we have there. From here, sine over cos is tan, so this brings tan squared plus, now we have cos over cos, this will be 1. So to end up with that negative, we can now move tan to the right, meaning that now we remain with 1 being equals to sec squared theta minus tan squared theta. So this is the identity now, where we have sec squared theta minus tan squared theta is equals to 1. Notice that that's this identity here. Now that we have found the identity that we want, notice that if we can define this to be, let me get our equation. This is our hyperbola. So to make our hyperbola fit what we've been given, what do we need? We just need to define the x to be equal to the sec and the y to be equal to the tan. Notice that if we did that, then this would be satisfied. So we then conclude that we'll then let x to be equal to sec theta and y to be equal to tan theta. If we did that, then this is going to be satisfied. How does this work? Notice that if we wanted to do the reverse, we'd first have to square this so that we get x squared is equals to sec squared theta, and y squared would be equals to tan squared theta. And to make it fit so that it comes back to this, that form, what we'd have to do now is we'd have to subtract x squared minus, so I've said this minus this, so minus y squared, and this on the right side would have sec squared theta minus tan squared theta. So by that same identity we derived, this is 1, so that correctly it gives us this is equals to 1. So have you seen Billington, a case where we would have to subtract? Have you seen it?
Yes, I'm just trying to follow now. Of course, I can see we're subtracting there.
Yeah.
But then, so whether we add or subtract the sec.
No,
So when
here
we
addition
have a
would
subtraction,
fail.
it's the sec versus tan.
Yes.
Oh.
Here addition would not work. Subtraction is what works here.
The cos and sine.
Cos and sine, we use addition. Okay. So here, I was just trying to prove our solution, but otherwise the parametric equations they wanted are just these. So everything that followed after this, I was just trying to show you that indeed these parametric equations combine to give us back that equation they gave us. Okay, so the actual parametric equations are the ones we came up with earlier. Sec theta and y is equals to tan theta. So these are the two parametric equations. Have you got that?